So Jay, thank you so much for joining us too from San Francisco. And first, can you share with us your background and your expertise in EEG?
Sure. This is my 41st year practicing in the field of EEG. And I quit counting at 500,000 records back in the 90s. And EEG is pattern recognition, so the more you see, the better you're able to see it.
Right.
And there are really only a handful of people that have seen that many EEGs. Most neurologists will get, in a busy medical center, 2 or 3 in a day, maybe 5 in a day.
Right.
So 500,000, that's a lot of days.
Fantastic.
So we had a laboratory that did 100 each day, and the numbers stack up very fast. So I have a lot of experience looking at the wiggly lines of EEGs. Luckily, these techniques have developed during my career. So instead of just looking at the wiggly lines, we now use fancy computer algorithms to draw maps of where content comes from. Historically, if you would have asked me, well, what's the likelihood of seeing the impact of a sound in the brain? Well, yeah, you'll probably see an impact in the primary auditory cortex. You see a little ripple in the pond of throwing the little pebble of sound in. But boy, it's pretty hard to hypothesize that you're going to have systematic impacts in more areas than just the primary area. And most traditional analysis would have only found that.
Right.
However, we're using modern computer technology and advanced science here. We actually did a technique called independent component analysis. We break the brain's activity into its component parts.
Okay.
And different locations are responsible for different things, and you'll see when we actually look at these components that the impact of these sounds is in fact felt everywhere in the brain, not just in the primary auditory cortex. So seeing a distinct response with a very limited number of individuals. Most of the time in science, you need a lot of people in a study because you're looking at one group and another group, and you have to separate the two groups. And the experimental effect is how strong that separation is. And usually you need 150 people, 50 people in order to see an effect at all.
Right.
We did a pilot study with 3 people. So if you would have asked me, what's the high probability of seeing a powerful effect, I would have said, well, pretty slim. We're going to need to collect more data before we can see an effect. But we can see the effect clearly even in this pilot study.
Wonderful.
So the effect is a strong effect, not a weak effect, or we would not have been able to see it at all, other than with statistics.
Right.
And you'll be able to see with your eyes, with no statistician, that these effects are there in the brain.
Wonderful.
In fact, we have a series of them created as images,
Okay.
so that we can actually look at them.
Good. And just before we go there, Jay, you were sharing that you brought in a special analyst from St. Petersburg, Russia, who's like the best in the world, right?
Yes, yes. One of my partners is Dr. Yuri Kropotov.
Okay.
He was the head of neuroscience for the Soviet Union when it was an intact union.
Right.
Now he's the head of his laboratory in St. Petersburg because it's now just Russian. So he's famous in neuroscience in a major way internationally.
Good.
And the techniques that he's developed, the independent component analysis technique, in fact, is the only way we have seen these effects. Looking with traditional analysis techniques, you can see there's something there, but it's all fuzzed over by the noise of the system.
Okay.
We were able to break the components into individual little pieces. And let's say one component might only have 1% of the total energy of the brain going on in it. Well, what's the likelihood of seeing a small change within this 1% if you embed it in the 99%? Not very good. But we're able to look at it in isolation and see the differences between the sounds in each component in a very detailed way.
Wonderful. We look forward to the images that
Sure.
you'll be sharing with us.
The first image that we see is, in fact, one I would not have expected. The dot that you see in the front of the head here overlies the anterior cingulate. And the cingulate is buried between the two hemispheres here. The orange stripe down buried between the two hemispheres in the fissure is where we're really getting this activity from. So it's deep, and it's totally unrelated to sound. So my first impression was not a highly likely component to see any difference in. But so the cingulate literally showed the difference between each of the individual sounds, which we did not expect. The next series here is related to the midbrain. The midbrain is a relay station. All of your sensory information, except for the sense of smell, goes directly through the thalamus, which is the biggest organ within the midbrain. And the relay here that you see to the back of the head is not just visual, it's sensory integration. And the sensory integration area actually shifts. The next slide is the same component, but with the person shifting their focus instead of the right to the left. And if you look at the line drawings, not the bottom, not the map where things are coming from, but the actual data set, when you see the difference. If I click back and forth between these two, you see the difference between focusing right and focusing left. There's a giant impact of just the shifting of your focus from the right brain to the left brain. And I would not have predicted that this would be a powerful, measurable, stable effect. Again, back and forth between, same component, but shifting your focus. And you can see the dance between the two sets of focuses there. This component is a frontal component, right frontal. Recently, there was some rather awful behavior. People that behave very, very badly, that are sociopaths or psychopaths. This is the area that's not working. And when this area doesn't work, people do awful, terrible things. And this area, in fact, is able to differentiate one sound from the next. And even with only 3 people, the different sounds have different spectral peak locations across the frequency spectrum. And this is totally unrelated to audition. You know, this isn't your auditory cortex in the temporoparietal junction. This is your right frontal lobe. This controls impulses and gates emotional expression and controls motor behavior and hyperactives. This area is impacted by the sound technology as well. Here's another location that's the middle cingulate. This is somatosensory integration area. Actually, this is slightly skewed to the left. From the right side of your body, it's encoded on the left side of the brain. And it shifts between states as well. Here, this is actually the left auditory integration area. And we'd expect this area to be involved in the perception of these components, these phonemes. So, in fact, you can see a shift in the left auditory cortex when you shift your attention left to right. The next component is a more complex one. It's spatially not isolated. This is the right side of the brain. It's not only sensory integration at the back, but it's also the right frontal monitoring area, and it also has a shift right to left. In fact, you can see there's a separate peak structure when you shift focus right versus left. We're actually getting different frequency peaks popping up. So we're getting distinct impacts. Here, we're looking at the difference between listening to the sound and vocalizing the sound. So this is the person listening to the sound. We're only seeing the listening portion of this light up. When he's speaking the sound, the lower half of that, there isn't a component. This component doesn't fire up at all when you're doing the speaking of the sounds. But it's there when you're listening. And you can tell, I mean, the upper half of that image is when they're listening, the lower half is when they're speaking. That component goes away. It just disappears. This brain component, the 19 pieces that you fabricate the brain's electrical patterns with, this one's missing when you're doing the vocalizations, but it's strongly present when you're listening.
Yeah. This is very important for me because I kept them all in darkness because I know a lot about the sounds, what A means or E means or U means, because everything is subjected, can be subjected to scientific research. Then only I can accept this, okay? Because I don't, there are these two experiments. Vocalization, you say, ah, and then you only hear. You think the sound, you hear the sound, you vocalize the sound, and then you can put the sound to a para stage, which is beyond thinking, beyond pre-thought levels. So when I was talking to him the other day, there is a significant difference between listening and vocalizing the sound. So all these are very useful for me to refine the techniques and then make it scientific, because I want to teach things very differently in a very concrete fashion so that it is a science, not philosophy.
Well, in school, if I had learned this earlier, it would have saved me a lot of studies, because I did science and philosophy. And my last year of school, I thought, when I was looking through the newspaper for a job, well, there's no listings for philosophers. So I figured, well, maybe I'll go in the science direction instead. So it would have saved me a lot of time and trouble. This component, you can see, goes away with the vocalization. It's there with the perception. This component is there with the perception, but not with the vocalization. So these pieces, the components that make up the brain's electrical patterns, some of them are there when you're listening only, and some of them are there when you're speaking only. But you can see dramatically in the data set that these sounds aren't just influencing one little spot in the brain that's the primary auditory cortex, which would have been a reasonable thing to think. But then that's the surface cortex getting in the way of the midbrain, isn't it?
Yes,
It's thinking instead of observing the actual data. The real data basically shows us that the entire brain is involved in this, not just the auditory cortex, and that it's very, very specific. Each sound has its own fingerprint when the brain's listening to it. And we don't understand this nearly enough. We've only started to look at this. I mean, an N of 3, most people would hardly even call it a pilot. It's a pre-pilot. This is an extremely powerful effect because we can show it with such a limited number of individuals. If you need 100 people to show the effect, you've got a very weak effect. This we can show with a handful of people. The sound versus the vocalization versus listening was done with an N of 1. This is one person. What we've seen here is powerful, powerful material. And the technologies that you've developed aren't just some little ripple in the auditory cortex. They're orchestrating brain function in the entire brain, including the cingulate and the thalamus and the cortex.
Yeah, I have no doubt about it, because